Um, Once we did the basis transformation, and we can also do transformation of operator, um, which is just doing it exactly the same way. Right now, I think let's just erase all this. Right, because you know, if you want to use a new basis, we might as well do the transformation operator also, because many equations are operator equations. So if you transform all the vector in the new basis, you probably need to transform in the operator in the new basis also. The text will use the Dirac expression to do that, to do this discussion, which is fine, but it's not strictly necessary. So you can say, you can define say if A is operator, A operator F will give you G, right? And now you do a basis transformation, just like what we did here. Just like this, you want the in the new basis, then so if you try to transform F from the old basis to the new basis, you need a U, right? You need a U. You need to multiply by U of F, right? Because that's the. But then to keep it the same, so you need to multiply by U inverse, right? So that's a U inverse times this identity matrix, right? And then to get the left hand side in the new basis, you also multiply by U. So, and then in the right hand side, this is U times U, right? So the U times G will be given by this UA inverse, which is just the U vector. That's a unitary. Right. So that means the operator in the new basis is using, you can express the the A operator from the old basis to the new basis by this transformation, right? Okay, so whatever A you get the matrix representation in the old basis, you multiply by U, and U that U is defined by this one. U is defined by this one, and then the U deck is just by exchanging this element and take the complex conjugate, right? And then uh, do this matrix multiplication and get the matrix representation new basis. So that's how you do it. And I mean, in the you use this direct expression, just like what the textbook did. So A is in the old basis, it's the sum of a new, and then the A new mu. Well, actually, well, the textbook you mu and new. Now this time, it used to use new mu. It doesn't matter. And then find mu. Right. That's the that's the expression of A into the set of basis of phi phi mu, right? And what you can do is to insert this so-called identity. So let's say that is equals to sum over mu and insert the set of phi nu and phi nu prime and nu prime. So that is what we call one in direct notation. So insert that, and then you have this the original one. A mu and phi mu. But then you want another one because you finally you want to express it. You, finally, you want to express it like whatever the new basis. So the new point, new point. You want to finally get that. So so after you do that, you have find new point. You have this one. And so you need another set of this one. So you probably can you're using new and what else do we need? Sigma. Yeah, sigma. 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 Right. And now we want to well, I missed the summation. This actually with the sum over both. Right. And finally, I mean the index will be different because this is over this is mu and this is over sigma. So you know it's sum over new sigma. And put this first on new point, right? And then there's there's one more sum is some of them mu, right? And then you have this dot product here. Now you are doing this trick, removing this part of the bracket. Regard this as a scalar product. New point, and then by new, not doing the same like this, and that it becomes a scalar product. And then so this becomes this one. So this becomes the the new matrix element in the new set of bases. And what you have is this is your U because of this you define U in here, and this is exchanging the pi and non-pi. So this and then the complex conjugate. So that's a U dagger. So this is A U times A dagger and give you A, right? And except that, of course, this is something from mu and mu. This is, but this is a sigma. So in order to do that, you need to kind of rotate this indices. But you get the idea. So, so this is exactly the same thing as I said here. So U decker will give you the new matrix element of the transformation matrix. Or no, the transformation will give you the new matrix element of the operator in the new set of bases. Okay, so this is how you transform operator. It's okay, yeah. A few minutes left. All right, so that that's fine. I think we cover up to this because my discussion may be a little different from textbook. Right. And so as a final remark in this section is this: sometimes as you are not using this this we have multiplied by the inverse, right? And then we change inverse to the dagger by the property of that the u is unitary. But sometimes we are just stay with this. If u is not unitary, so u inverse is not u dagger. We'll just stay this. So this is what we call g prime, right? G prime is a prime. This is a prime. So the whole thing is g prime is u is a prime, and this is f prime, right? So a prime is this u a u inverse. Without this, this is not your dagger. Okay. That is sometimes we do that also. This is so-called similarity transformation. It's not unitary transformation, and so that's the it's not like a basis transformation like what we did. For basis transformation, you get this is U inverse is U dagger, but then similarity transformation doesn't have that. Um, Sometimes it's useful to have this kind of transformation also. So that's for now. It's terminology, and we can see some example for applications. The textbook example is using this to apply to the Gram-Smith uh, method, and to show that the Gram-Smith procedure is not unitary. You transform from a set of function to and then normalize and make it a orthonormal set. And this transformation is not unitary. That's this example is about. Mm, what else? I think it's time. Yep. Anything else?